Okay, for people who are joining this live stream, sorry, we're starting slightly late. We are going to look at some things to do with non-deterministic Turing machines. And the reason for doing that is that they're kind of a minimal model, both for some questions in quantum mechanics and for some questions about distributed computing. And to remind ourselves how non-deterministic Turing machines work, actually somebody is asking a question about causal fermions, which I have never heard of. So I'm going to look just for 1 second at what those are, just out of curiosity. And then this doesn't seem too relevant. Maybe, I don't know. Anyway, not what we're going to look at today. Well, maybe this is more relevant. I don't know. All seems to be the work of one particular guy. I have no idea. No, nothing. It's kind of an odd page. Yep, don't know. All right, we'll send this off to our internal group and see if anybody can make anything useful out of it. All right, I'm going to come back to non-deterministic Turing machines, which is our subject today. So this is a typical example, right? We've got this involves two different Turing machine rules, and they can go from this initial state to a variety of final states. And one of the questions is, so here I was looking at Turing machine rules that should have the feature, wherever B8 is, that should have the feature that we're looking at rules that differ only by one bit from each other, so to speak. People understand what I mean by that? So here I've got this particular Turing machine rule, right? And I want to add, please do respond here, guys. And I want to make this non-deterministic by making one of these cases have two possible outputs. Do you understand?
Yeah.
So the thing that I realized, so if you do that, there are 131,000 different possible Turing machine rules, and these break into, I forget how many it is, but I had worked that out in this notebook that we can't open again for some reason. How many, maybe I should just start it up in another session here to see whether I can get that thing to open. Let me just see whether that works. Oh, great. Let's just try this and see whether I can separately get it to open and then just copy over the relevant pieces. I think it just got very big with lots of okay, so hold on, let me just go and say open. Hold on here. I want to go and get that out of the place I originally had it. Okay. Okay, it's hanging, but I'll see that that finishes. Okay, so what I was doing here is looking to double one of these things, okay? And then asking the question, what does the multi-way system that you get when you do that doubling look like? Am I making sense? And what we found was all kinds of exotic multi-way systems. So here's a case where it branches, but only after a while. Does that make sense?
Yeah.
Okay. So the next thing I want to do is I want to consider Turing machines that actually halt, where some of these cases simply don't exist, where if you get to that state, it just stops. That would be the analog of that would be the analog of what we've done with string systems, where they simply, where there's no applicable rule and they simply terminate. Does that make sense?
Yeah.
Yep.
Okay, so the first thing I want to do is to look at Turing machines. I don't know whether our built-in Turing machine function deals with that generalized case. So let's find that out. So if we have a case where, and how we might represent the case where it just stops, right? And I think, and maybe what we can do is we have offset 0 here. Maybe that would represent the Turing machine just stopping, right? If we have the same color and offset 0, then the Turing machine will not evolve. I don't know whether multi-way Turing machine will do the right thing at that point. Does that make sense?
Well, it will probably create a self loop in it. But given that it deduplicates states, it shouldn't. I mean, it should be fine.
Okay. Well, all right, fine. So then let's do the following. So what I had done here was this is using this representation of Turing machine rules. Okay. So, and I've been getting these pairs that represent a rule and it's 1 bit away rule, and combining those to make a non-deterministic Turing machine. So the first thing I want to do is to look at halting versions of the 4096 two-state, two-color Turing machines. And then I want to extend that to looking at cases where they are non-deterministic. Does that make sense to people? Do you understand what I said, or should I repeat? Okay.
Could you repeat that?
Okay, so we're trying to figure out, there are 4096 two-state, two-color Turing machines. Okay?
Mm-hmm.
If we allow for halting as well, there will be an additional set of sort of below two-state, two-color Turing machines that have smaller rules than that. See what I'm saying? Because some of these rules will now not be present. Did you get what I'm saying?
Yep.
Okay, so what I want to do first is enumerate all the possible sub-2-2 Turing machines, so to speak, just to see what they do. And then what I want to do is, what I was doing before was I was looking at the in a sense, 2-2 non-deterministic Turing machines by adding one additional case to a 2-2 machine. But what I realized is there's actually a smaller case than that, which is adding something to a halting below 2-2 Turing machine. Does that make sense?
Yeah.
And I can already see that among the 2-2 non-deterministic machines, there's plenty of interesting stuff that happens. Oh, whoops! My crazy thing finally came through. Okay, so what I want to do here, let's redo this computation and not have it generate this absolutely vast. Okay, so what you can see here is there are all kinds of interesting, non-trivial cases here. So let me do the following. Let me say, okay, so what you see here, these are let me just close that up because oh, come now, don't get jammed. Okay, so these were cases of non-trivial let me copy those in here without that giant cell that I think will help get everything stuck. Okay, so this was the down here. Okay, let's go here, and then let's say to that semicolon, and then let's go down here, because these are some of the interesting cases, and I want to just look at some of these cases for a minute. So these are cases, again, the 2-2 non-deterministic cases. Make sense? Yes, you understand what these are? Whoops, why is that doing that? Oh gosh, don't tell me this thing is going to spin like crazy again. How could that be? Well, maybe there's one of these that's absolutely huge. I don't know. This thing is like, 55 megabytes of detailed graphics. So maybe that's what's causing us trouble. Okay, hold on here. Okay, let's see if we can get this in here. What is going on? Why is it doing this? Oh, by the way, I hope somebody took that other thing, because I just deleted the cells that caused the most trouble.
Yes, Danielle already. Danielle sent the Dropbox folder. I'll check to make sure that
Well, somebody
the link still works. Yeah.
No, but I modified the file.
Right.
To remove so it won't now. Okay, what's going on here? Oh, for goodness sake. Okay, maybe we need to get somebody from that team in here. This is crazy. It's just complete.
John specifically?
Well, I don't think he's around, but okay, whatever. This is just crazy, absolutely crazy. Okay, the question is, what is causing this to hang up like that? It's really weird. And is this file huge? This is a new issue with these graphics. Is this crazy thing with this dynamic location stuff? I'm going to send this again. I think there's a way. Does anybody know how to switch off the dynamic location stuff for these graphics? Maybe these graphics all have this performance goal arrow quality set. Am I making sense? Do you know what I'm talking about? Anybody know what I'm talking about? Mano, do you know what I'm talking about?
No, sorry.
Really? Didn't you use that for a bunch of the graphics that you made?
I did not.
Really? Well, my machine has now lost its mouse, so that will not allow us to do much here. All right, did somebody else manage to look up whether Turing Machine supports things where the head does not move? No? Well, I'm not in a position to do that because my machine has lost its mouse.
Working on it.
That's kind of an amusing problem. When this thing is hung up like this, literally there's no mouse. You can't, mouse does not respond and is invisible. So, kind of interesting. Dead reckoning. It's a ghost mouse. Wow. It's really kind of an interesting problem.
If you'd like to force quit Mathematica, you can do that with a...
I'm well aware of how to force quit. Thank you. I'm well aware of how to do that. Thank you.
It's the first thing you learned.
Not quite. That's not really okay. See whether we can reach John.
Yeah, I'm here.
Okay. Have you any idea what's going on here? I scrolled down in this notebook. I removed a lot of the more complicated graphics. I'm scrolling down in this notebook. It's just hanging like this.
Well, okay, so it looks like it just disappeared. Is that right?
Yeah, except my mouse is not back.
Yeah.
Look, the file menu. See the file menu? It says
Mhm.
saving 84%, 96%. Okay, so which graphic here? Okay, so these graphics are not particularly big. So I think it's this dynamic locator nonsense. What is that thing? And how do I get rid of it? I mean, this is very bad, what's happening here. Okay, so this window lost focus, right? Even though I'm clicking on it, it's not in focus.
Yeah, you might just be able to switch back and forth and have it come back.
Nope, didn't
Nope.
work. Didn't work. Totally hosed.
Well,
Okay, so let's look at these graphics and see whether we can see which one is causing this trouble. Because these are not big graphics, as you can see.
I mean, it may not be a single graphic. It may have been, yeah. Is this
Well, I deleted, what's that?
Is this a notebook you were editing or a notebook you were composing?
No, I was copying from another notebook that had just a ridiculous, that took 10 minutes, you know, with the spinning disk, okay? I'm going to quit this and I'm going to restart here.
It's probably a good idea.
But I mean, we've had this problem ever since 12.2 has been, you know, ever since sort of the end of 12.2, we've had this problem. Okay, so let's see what happens if I scroll down here. Okay, it's just frozen. Oh, but it came back here. Okay, so now it managed to scroll through this decently. Not great, but decently. Well, you know, maybe there was something left over in the cache from a previous large graphic that was there.
Well, yeah, I mean, without having seen a little more of the history of this, it's a bit difficult to usefully speculate.
Okay, well then you should be able to get the previous file. I deleted some stuff from that file, but it could be recreated if necessary. Okay, we need to get on with what we were doing here. So
okay.
I mean, yeah, we'll call you back if this fails again. And I don't know what.
Sure.
This is another failure. I don't know what's happened here. This is probably not your failure. This is probably a graph rendering failure. Okay, all right. Well, thanks.
Okay.
Okay. Okay, guys, what was the answer about Turing machines?
So the question.
Did you understand the question? Do I need to repeat the question?
Yeah, if you specify the rules explicitly, then you can put zeros there and it doesn't move the head.
Okay, fine. That's what I needed to know. So what we need to do here is to write something that will enumerate the cases of these rules with and presumably, can we overstate the rules? No, we have to do that in a multi-way system. So what would we do here? What we would do is we could put every individual case of the rule in the multi-way system, right? Maybe that's how we should do it. Maybe we should just state these rules for the multi-way system in, do you understand what I'm saying? I'm trying to figure out, how do we give, do you understand what I'm saying? No.
I don't.
Okay. Does anybody know whether we have the thing that will convert from a numerical Turing machine rule to the explicit form? Is that in the function repository? I know we were supposed to have something like that.
Turing machine from number.
That sounds right. Oh, here we go. Here's one. Okay, so that's the form of the rules. Okay, with states 1 and 2, and I guess this is saying that's the color on the tape. Am I making sense? So each of these subcases, let's just write something which enumerates all meaningful cases of the Turing machine. Okay, do you understand what I'm saying? All these sub pieces in the Turing machine rule, right?
Yeah.
Okay, can we just figure out what that should be? So I think it's just table. So there's a state S0. There's a color C0 going to a state S1, a color C1, and a direction D. Let's say an S0 goes from 1 to 2. S1 goes from 1 to 2. C0 goes from 0 to 1. C1 goes from 0 to 1. And D is -1 or 1. Is that right? And there should be, okay, there we go. How many flattens do we need for this? 1, 2, 3, 4. Yes, is that right? Oh, actually, I didn't. I could have flattened all the way because it's just going to be these rules. Okay, so this is our rule cases, right? Let's see whether if we just take 2 of these at random, for example, those 2, I wonder whether the Turing machine function, I wonder whether this will work just as a way to get graphics of these things. I wonder whether the rule plot works in this case. Dang. Can somebody look and see whether they can figure out how to get, is there a version of rule plot that can work? I wonder whether this works.
I remember there was a way to jailbreak it, but I don't remember for this case or not.
We should simply have this work. I mean, this is silly not to have this work. But yes, if we can figure out how to jailbreak it and make this work, that would be good. So now let's try and see whether it works. Okay, so here for the Turing machine, this case here, I think what we're going to want is each one of those is going to want to be a full Turing machine specification. I mean, this isn't a very exciting case, but let's take this. Let me just modify one thing just so it does something. 1, 0 there. Okay. We got to figure out why those graphics are so broken. But okay, so let's just see if this did the right thing. I am almost completely confused here. I would have thought it would start in this state here. Do you see what I'm saying? And then why would there be a back arrow from this state? Oh, by the way, does anybody know how to get this to work better with the silly thing with these sizes? Do you understand what I'm saying? See that? Mano, do you have any idea how to make that work better?
I can try to take a look, not off the top of my head.
I mean, maybe it has some absolute size burnt into it somewhere. I mean, I would have thought the vertex size would be determining. Yeah, that's not helpful. Because it seems to have an absolute size for the head and so on. Okay. Well, even though we can't, we need to know how to display the rules. But let's go ahead and look at now what we want to do is we want to enumerate. So we've got here okay, 32. So that means of these, there are 2 to the 32 possible sub 2-2 Turing machines, if I'm not mistaken, right? Am I right? Am I wrong? Is anybody there?
That seems correct.
Okay, then please say that. Please get yourself off mute and talk. Otherwise, I might as well be doing this on my own. Okay, that's a lot of Turing machine rules. So let's see whether we can reduce that, because what we want to know, I mean, okay, so many of those rules. So for example, if we're starting off with a blank initial state, we know that we certainly need a rule. We certainly need that rule to be present. 1, 0 goes to whatever. Am I making sense?
Right, and we should also make sure that any rules we select at least mark the tape once. Otherwise, we'll just get blank tape.
Okay, so let's be very concrete. We've got 2 to the 32 possible rules. We want to prune them down. Okay? So, I mean, for example, one thing we can do here is let's do a random sample of rule cases. Let's take 5 rules from the rule cases. Okay? Now let's take this and let's see what we would get actually if we take this. Now, presumably for the multi-way Turing machine, I could treat each one of these as a separate Turing machine, right? Guys, are you there?
Yes, seems like you should be able to do that.
Okay. So again,
You have a null as the first
yeah,
argument.
I know. Okay, so then this is the Turing machine specifications, right? Okay, so that didn't do anything, which is not too surprising because it probably didn't have a 1-0 case. Am I making sense?
Right.
Yep.
Okay, so let's go. Let's make, I don't know, 20 of these. And then let's say, for these, I want to take this. I don't know whether I really should put in some protection. Does multi-way Turing machine have a way of kind of quitting if the thing gets too big? Does it have a mechanism for that? Do you understand what I'm asking?
Yeah, I'm looking.
Okay.
It doesn't look like it.
It's something we might
And
want.
also, some of the examples from the documentation also seem to be broken in terms of the vertex sizing. I feel like that's something.
Or maybe something broke in 12.2. Maybe 12.2 has changed something. So then we need to track that down. All right, let's try this here. Okay, so here are a bunch of random 5-case non-deterministic Turing machines. Make sense? It's kind of interesting, actually, that there are ones that don't die out. Do you think that's sort of interesting? I mean, so let's take this one and this one. Let's look at those. I mean, this makes me think that we should look at just the ones that have even fewer cases in the Turing machine rule. See what happens with them. Because, you know, the minimal case, the minimal non-deterministic case, I mean, can we see what the minimal case where we can get, for example, a tree is? My guess is the minimal pure tree is just a very simple, it goes left, it goes right. No, that won't give a tree. That will give a grid. Am I right?
Right.
So let's try that case just to make sure we understand what's going on, okay? Okay, so that case would be...
Well, I mean, you need to specify what kind of tree you want, because well, you can obviously make a trivial tree very easily.
No, but let's find...
change a color.
Let's see if we can make a... oh, I see what you're saying. We could make... Okay, so let's do the most trivial thing where this goes to state 1, right? And it writes a 0 on the tape, and it goes -1. And then we have the same thing.
Yeah, in the other direction, it changes the color, so it terminates.
Why would you want to change the colors in the other direction? Why not
So
just...
because if it keeps moving in the other direction, it's not going to be a tree, right? Exactly.
Okay. So minimal case. Okay, so this one is just move left and right. Okay, so now what you're saying is, let's say I change the color. So what are you suggesting? That I change the color here?
Yeah, just one and try variation.
You are right. So then
Yeah,
this...
so you just give it a chance to terminate at every cell.
Okay, let me just understand this if I go a little bit further. What's happening here? So these termination cases, I see the termination case. Right, I see this. Okay, so this, in this case, it can terminate at each step by going to the right and writing.
Actually, it's a bit more complicated because it doesn't change the color of the destination. So it still keeps going for a while, but for some reason it still ends up being a tree. Well, I guess because it cannot return back since there's now a barrier on the way.
Okay, well, let's try some other minimal cases. Okay, so what happened here? Oh, there's that stupid show in there. I don't know why that show is there. Should get rid of the show. Get rid of it here, otherwise we'll get confused every single time. That one has a show as well. I'm going to get rid of it just for the sake of... Oh, and this will actually, that will mess this up because this will give a different random set, but it's okay. All right. Oh, that's a fun one. Look at that. See, that's interesting that there's already something pretty non-trivial happening, even in... Okay, so let's try this case. Oh, for goodness sake, what did I do wrong here? Oh, what did I do wrong? Do I have an extra level of list bracket? I think I have an extra level of list bracket. Okay, let's try this for a few more steps. Let's try this for layered. Just for a few more steps, just for fun. Okay, so we need to understand what something like this is doing, but it's interesting that we can get that. But let's go ahead and look at the cases where we have, where we're picking just two. In the case where it's, so it's, how many is it? It's 32 choose 2, isn't it? Cases. Am I right? That's the number of cases where there are just two. Am I right? Do you understand what I'm doing?
Two rules.
Yeah. 2 rule cases. Okay, so there are 496 of those, so we can just enumerate those, I think. Let's just look at them all. Okay, so here are the rule cases. So we want to just take tuples, if I'm not mistaken, of rule cases, comma 2. Am I right? Is that right? Is that right?
Subsets. Because you don't want the same one twice.
And then how do I do that? Is it list 2 there?
List of 2.
Okay. All right, good. Okay, so now let's go ahead and compute this. But I think what we want to do probably, and I might, do you think I need to use it in parallel? I think I probably need to do a parallel thing here.
Do you need another list to turn them into separate Turing machines?
Yes, thank you for pointing that out. Okay, hold on 1 second. Okay, that's that. Oh, I've got the list there, list slash at that. So this is now list slash at, and then I can say subsets of rule cases, this thing, comma 2. Do you agree? And then this comma 20 is irrelevant. Then that's closing for that and closing for that. And I think
Let's
I might
show the list is at the right level. Because each rule needs to be
you're
in the
right.
list.
You're right. It's map list at level 2. I mean, alternatively, I could do that by taking, actually, you know what I should do? Instead of doing it that way, I should say list slash at rule cases here. Is that right?
Yeah.
Okay. Okay. So now, and let's actually make these, I think I probably want to make these image size small. Maybe even tiny. And let's give it a whirl. So again, I predict there'll be nothing very non-trivial that happens here. Anybody else want to offer an opinion? I'm wondering whether go.
Because if rules have the same left-hand side, then it has to always have the same color.
Oh, you can't be serious with this first thing here.
I know the rules are different, and it's truncated ordinary Turing machine.
Okay, let me fix this problem. That problem probably comes from some machine having, what the heck is this? Failed to find resource. That's one of the parallel machines didn't have let me just try running this again, just because I'm curious whether the same error will occur again. Whether it was a race condition. Yeah, I think it was a race condition from. Okay, so let's take a look at this. So this is showing that the most that occurs are these kind of binary, are these trees. So like, let's say here, that's a slightly non-trivial tree, but it's a pure tree, right? Is it obvious that these things can never merge? Do you understand my question? So there's no merge.
Well, they can merge in one case where there's the same color and you can go left or right.
I see. So there should be one case which I think already saw, which we generated by hand, so to speak.
Yeah.
I mean, that case is a trivial merge. Let's go ahead and do the following. Let's go ahead and take this.
Where is that case? Oh, that's the first one, I think.
Yeah, I think that's right. Let's go ahead and enumerate the ones that have distinct trees. Okay. And what's the best way to do that? Canonical graph is probably too slow. Maybe we should just enumerate them by virtue of what the what the growth function is. So in this case, we could evaluate the growth function in each case. Let's look at the distinct growth functions.
Are you sure canonical graph is too slow? Because these are pretty small.
Well, these ones probably wouldn't be too slow. All right, let's go ahead and do canonical graph for this. Okay. So what I want to do is I want to say parallel monitored of this, and then what I want to say here is canonical graph. And then I want to say, for the whole thing, instead of that, I want to say gather by first of the thing, right? And then what I want to say is, let's say, for each of those, I want first of hash, and then I probably want length of, no, I want first of hash, right? Length of hash, and then maybe I want first, I want hash sub 1 comma 2, let's say. Let's hope this isn't like hanging up in canonical graph. I have a bad feeling about this. There's some that are not so small here, like that. Yeah, this is not good here. All right, this is not useful. So let's put a time constraint there. Let's say 2 seconds. Let's try it again. Okay, so those are the distinct. We don't know what the aborted was. I think that big tree graph. Should we let's okay, how many were aborted? 4. Okay, we should probably look at what each of those was. I bet that's these ones. Okay, we got to look at those explicitly. How do we want to do this? Max, do you have a good idea how to do this where we abort? Do you understand what I'm asking?
Yeah.
I mean, I suspect that the growth functions will make them unique, but I think we should be careful and not lose any. So I think in this case, what we should say is, I mean, the correct thing to do is with this, it's either time constrained maybe we can use the enclosed confirm stuff here.
Let's see, if it doesn't exceed, we just don't do canonical graph. So in other words,
no, I understand.
This is the result of the resource function.
Yeah, okay, fine. with that, so we say, I think we want to say confirm time constrained of a canonical graph of G. Oops. Comma 2 seconds. And now, then the question is, what happens? Okay, so now we want to close that with. And that 2 is wrong. Okay, now we want to say, if the confirm fails, so then we want to put an enclose
Actually,
here.
time constraint has a third argument, which is fail expression.
Oh, that's nice of it. Okay, that should then work. And let's and each one of these we probably want to say graph image size arrow tiny. Okay, good. All right. So this has some slight issues with canonicalization, but that's basically the right story. Okay. All right. So those are the cases that's the cases for size for 2. So I think the next case we have to look at is probably 3. Okay. And I think we just have to do it. I don't see that there's much choice about it. Do you agree? Is there any reason not to do it the same way? Guys? That's binomial 32, 3. That's still civilized. All right, let's try it. Okay, what do you predict is going to happen here? Is it going to be non-trivial or not?
Hard to tell.
Let's hope we don't have thousands that hit the 2-second timeout. Okay, let's see whether this can render. Okay, let's take a look here. Oh, we got some nice ones. That's a nice one there. Okay, that's one that I saw in the... Okay, so these are trees of trees, effectively. Maybe. All right, let's keep going. Okay, there's one. It's more interesting. Okay, so there's several quite kind of interesting ones here. So let's take a look at some of the more interesting cases. Okay, so a lot of trees of trees. Basically, trees are happening when the system can't re-interact with itself again. I should have done it with an interactive selector thingy. Okay, let's go keep going here. So that's another one of these. Can you tell what's happening in those? Are those going to keep going in a grid, or are they going to give up? Let me just see. This is... Okay, so that was one sample there. So we want to just copy out those single samples. Okay, so that's an interesting one.
It can move twice to the left, once to the right.
Okay, so then it's going to, poop out at that point. Is that your claim? Do you think this one is interesting?
Might be. let me look at the rule.
Oh, sorry. Any interest in this one? Or is this just going to go in two different distinct directions? I better copy it out just in case.
One thing to consider filter out is when it has n vertices and n-1 edges. That'll get rid of all the trees.
I don't think they're pure trees. And what the heck is that one there? Isn't it amazing that we can get complicated stuff even with these just such unbelievably simple situations? What about that guy? Is that just a tree?
At the center.
What's that?
Not at the center, it's not.
Yeah, but maybe it just goes it trees out as soon as you've got a little bit away from the center.
No, it's not.
Okay. Well, that one I need to.
Oh no, it's not. Yeah.
Not what?
Not a tree.
Okay. All right, let's get this guy here. I got to be a little bit careful because I want to take that tree as a separate case
I
here.
think this one is a line if you run it for longer.
Okay. Hold on. I just want to check that I've got this structure correct. That's probably not interesting, but let's get it just in case. I think I got this wrong here. It should be that. And this guy is the last interesting case, I think. Actually, I want to just look at what that one does. Is that thing at the top interesting? The
Could be.
Okay, fine. Let's look at these. Now, did I type these in wrong? Am I? Oh, shoot. Look at that. That's definitely like that. Did I get this right or did I get it wrong? Okay, so that's that. Let me just check one thing. If I just say framed here, if I just say length / at that, good, they're all threes. Okay, all right, let's try this then. Okay, so now I want to map it over this. I don't really need all this rigmarole. I'm just going to look at each one separately. No gathering stuff and no canonicalization stuff either. So I just want to say graph, and I don't even want tiny there. I just want to say G here. And I wanted, let's say, 7. And here I just want to not have that at all. Okay, let's try running a few more steps. Is this interesting? Is this going to be? Boy, these are so complicated. Okay, let's try running a few more steps. I may regret this. Let's try running 10 steps. Okay. Okay, so let's take a look at what we've got here. So these ones, my gosh. It's probably basically a very slow Fibonacci tree, would be my guess. Am I making sense? I mean, in other words, it's got a lot of lag, but it's ultimately just going to make new branches.
Yeah, you might want to try taking that first one and seeing how many nodes are in the 5th, 6th, 7th, 8th, 9th, 10th steps.
Okay, so let's actually run this with a. Do you know if multi-way, Mano? Do you happen to know if the multi-way thing supports a different graph layout? I'm sorry. Wow. Wow. You know, how can I be surprised after 40 years of doing this when yet another system turns out to be capable of pretty complicated behavior, even from very trivial rules? That's just crazy. Look at that thing.
In that one, that complicated, why is the graph flavor had a really wild line on top?
In the graph layout.
Yeah. What is that top line?
Yeah, I understand.
Between...
Why on earth is it wiggling like that? It just makes it's an artistic line, but it doesn't make a lot of sense.
Maybe it has custom rules for how it should go to each next layer.
All right, what's going on in this picture? So what we clearly want to do is to label something about the Turing machine. So for instance, if we look at this Turing machine, we should be able to see, I mean, this is a quite non-trivial object here. I wonder whether the number of, let's look at this thing, just the states counts list thingy, okay? What's it called? Is it called states counts list? Is that right, guys? Could somebody look that up, please?
Yeah, it's correct.
Okay. Okay, so here I want to say histogram. No, not histogram. I want to say list step plot of this. Let's just do that for now. And just to make it more beautiful, let's say filling arrow axis. Well, I think we probably want to do differences here. That's a bit surprising to me that these are all so trivial.
And more steps, perhaps.
Well, okay, fine, let's try it. Well, maybe these things are less complicated than we think. I mean, let's take a look. How can that one? Look at that one. So that one, according to this, just goes up by steps here.
There's a differences.
Yeah, those are differences. So it's going up quadratically. Well, let's look at the actual sequence. Maybe what we want to do here is to just do find sequence function on the actual sequences. Is that a crazy thing to do, or do you think we should try doing find linear recurrence? Anybody got an opinion?
I'd do linear recurrence to start.
I'm a bit confused with it because there is a linear number of states. There. Oh, hold on. No, never mind.
Okay, so the answer in that second case was it is a recurrence. It's a third order recurrence. Okay, so a bunch of these are third order. These ones that go up in steps like this are third order occurrences. So let's take that last case. Well, it doesn't look very exciting. What's going on in this case here? Can you tell? So the other thing we could do as an indicator is to look at, for each layer here, for each step here, we can look at what the distribution of head positions is. Am I making sense? Do you understand what I'm saying?
Yeah, what does that tell us?
It's some indicator of what's going on. I mean, like if it's a uniform, I don't know. I mean, they may be simple distributions. They may not be simple distributions. Let's find out for these cases. So again, reviewing again here. See, like this.
I think it's really important to look at the rules, because we might just be able to understand what they're doing.
Okay, well, fine. Do we have a way to display the rules, guys?
Well, not right now. I remember I sent you an email a long time ago about how to do it, but I cannot find it for some reason.
What should I search for? Turing Machine or something, or rule plot?
Well, it had some variation of the word jailbreak in it.
Okay, well,
it might have been inside a notebook.
Do you think you spelled jailbreak as one word?
I'm not sure.
I found one thing here. Let's see. No, this is a Turing Machine state rendering function. You could just go look at the actual source code. You could just get one. Wait a minute, this must contain something here. The Turing Machine state rendering function must contain, oh no, that's the state, right? It's got to, and this, by the way, is whatever the mistake is with sizes must be present here. And we could just go look at that in the source for the state rendering function here. Okay, what the heck do you think this thing is doing? What is this doing? Can you see what this is doing? I mean, one thing that's true here is that these are one thing that's interesting about all these ones is that they're all one state. Well, at least this one is a one-state Turing machine, basically. So actually, that's an interesting case. We should look at, okay, case to look at, one-state NDTMs and one-color NDTMs.
I think I found it.
Oh, okay, good. Ah. This is totally frigging weird, but what do I do with this?
So just evaluate it, and then it should start working if it's the same case.
Okay. All right. Let's do this then.
I mean, it's just modifying the internal code for it.
Okay. This is Max's magic TM rule code. All right. Let's see what happens. My gosh. So why don't we just fix that? Let's do a packlet update and fix it. Okay, can you send that in, please?
Yes.
No, you can't. Max has to do that. He's got to explain.
Send to, you mean open a PR with it?
Yes.
Okay.
Yes. But preferably, if there's a Packlet update that's possible, we should do that. Am I making sense? Do you understand?
Well, I don't know. I mean, I don't know how it's deployed.
I don't know either, but send it in and send it to whoever, I think it's Jose, maintains this particular thing, so send it to him. Okay, so let's go back down here and wherever it was. Why don't I just reevaluate this with a Turing Machine rule plot wrapped around this? And by the way, obviously when that's changed, we should change documentation to make sure it records this. Okay, let's go ahead here. What? Oh, I see what happened. What I want to do here is in the Turing machine, I need to basically say flatten this. Because it's pretending that it's a non-deterministic Turing machine. Okay. Well, want to offer some opinions here about what's going on? My gosh.
Yeah, so it can go right once, or it can go to the left twice, which is why it's a line. So if you plot it in the previous way, you will see it's I mean, it did actually plot it before.
Which previous way? So I mean,
so basically, you can jump 2 steps to the left, or you can jump 1 step to the right.
Okay.
Essentially, and that's a combination of those.
Maybe what we need to plot is the possible paths for the head. But what this is suggesting is that there are already non-trivial things with just one state, which I find very, very surprising. But we should figure out what there is with one state. Let's go ahead and do that and just enumerate all the one state Turing machine instead of a 2-state Turing machine.
Oh, I see.
So if I go to
the head state.
Yes, one head state. So that means that S0 and S1 just get like that. And then this is rule cases there. And then what we want to do is we want to say subsets. So now we can do up to so there are 4 cases presumably for each of those. And then presumably we can actually, in this case here, we could just go ahead and look at all possible subsets, right? Because there are, how many cases are there here? There are a length of 8 cases. So there are 256 possible rules, right? All right? Subsets, there are 2 to the 8 subsets of 8 elements. Is that right? Ed, anybody else? Are you there, Ed?
Yeah, I'm looking at that.
Okay. I think there are 2 to the 8 cases. Is it not the case
that sounds right?
That we just want subsets of this, right? That gives us all.
Subsets is 8 times 7.
No, it's not. That's subsets 2. I'm saying all possible subsets. The power set.
Oh, that would binomial 8 too?
But it's not 8-2. I'm saying all possible subsets, right? That's the case. Is
Oh,
it?
I see.
Actually,
Yeah,
this-
2 to the 8, yeah.
Oh, yeah. Yeah, I see.
Okay. 256 of those. By the way, I just want to make one change up here. I just want to reevaluate this so we don't get confused. Okay, so then in those 256 cases, let's go ahead and do, should we do just this computation here? Yeah, we do want to do this computation here for those 256 cases. And now, actually, I want to say list / at rule cases 1, and then I don't want the brace 2 here, right? Oh, for God's sake, why is that? What the heck is that doing? I wonder if multi-way Turing machine behaves badly if it's given a null list initial condition, a null list for the rule. Somebody check that. Somebody check that, or should I check that?
Oh, I'm checking.
Well, it shows an error message. It's,
I know, but why is it doing all this nonsense here?
well, this looks like it crashed.
I can see that.
I mean, there are many things that can crash here, not just Turing Machine.
Well, I mean, this could have gotten too big. That t equals 5 might not, it's not obvious how big these get. Making sense? Because it could have, think about this, it could be a 2 to the 4, yeah, it could be a 4-way tree at every, is it 4-way or even bigger than 4-way? Do you understand what I'm asking? I believe it's a 4-way tree. So it's 4 to the t.
Right.
4 to the 5 is otherwise known as something fairly big. Let's quit this.
1024.
Well, that's not that big. Okay, this is crazy. It's just completely crazy. Come on.
Once it crashed, it's pointless waiting for it because it will just keep redoing it.
You think the same kernel will be running multiple times?
I mean, it will try to rerun the same case, I think, and then it will crash again.
Okay, all right, fine. It doesn't look like there's anything to do here other than to just quit this. Kind of annoying. Okay, let's do the magic fix again. And then let's go ahead and do, let me go ahead and do this case here.
Before you do anything complicated, can you just try running this one example with rule plot? Because I'm wondering if you evaluate it before loading the packlet, potentially it might not work.
Okay. What does that?
Yeah, so run the fix again. So it is probably a packlet.
Okay, that's a good sign. Means we could update it. Okay. All right, so let's look at this now. And then what we want to do here is let's use this thing. Oh boy, so many of these. Okay, let's look at this. Let's use this thing here. And let's, oh, I'd already done that. Okay. And then let's go ahead and say time constrained. I want to just say resource function. I'll be so happy when this is built in. Okay, so now here, do you agree what I should just do is say time constrained, let's say 3 seconds or something? Do you agree? Do you agree?
Sure.
Yeah, let me get, actually, let me
I mean,
do
if you
this.
want to prevent it from crashing, you probably need memory constraint rather than time constraint.
Well, let's not worry about that for right now. Let's see if we can get this to work. Rule plot of Turing Machine of flatten of hash. Oh, I goofed up here. I goofed up. That was a stupid thing to do, what I just did. I might want to kill it because this is going to show. Let's see, let's let it load in and then we'll kill it. If it works, well, let's just let it go. It's going to be a little bit goofy because because the right-hand side's here. Why is it taking forever? Because there's some absolutely giant trees, and this is going to cause us trouble with rendering again. Sigh. We have to figure out how to prevent this from causing trouble with rendering. I mean, maybe I can just say if vertex count is greater than such and such, don't render it. Anybody else got suggestions? Guys, you're really silent. This is just driving me crazy. I'm again, it's like, okay, let's pick up a few of these that look interesting, okay? And if Ed, please pay attention so that you can actually help in.
Oh, I'm finishing.
Okay. Okay, that one looks like it might be interesting, although I think we've seen it before.
That's the cones one we looked at earlier. Yes, that one's definitely interesting.
Are you sure? Or is that not just a big tree mess?
Oh, it looks interesting. It's got
That's not a
some
tree.
unusual symmetry that we haven't seen much of.
Is that the same as we had before?
Looks
that
like
the
it.
same as we had before?
Looks like it.
These I've seen. I saw them in the study of Rullial Turing machines. Something extremely like this. I think they come
Yeah, but
about.
that was all rules.
I know. I don't know whether these ones are interesting. Suspect not.
That one near the top right, I'm not sure what's happening. No, the next one, the one that looks like a line.
I think it's just back and forth.
Oh, I see.
Why did that work? Copy. Paste. Okay, that was less exciting than I had hoped because of the fact that it's but it is interesting that the ones, I mean, I don't know, for some of these, like, I don't know, let's take this one here, for instance. Yeah, by the way, notice that I was right about that being the Rullial case. That's an S equals 1 Rullial multiway system. See what I'm saying? Do you understand what I'm saying?
Can you explain that a bit more?
Rullial multiway system means it uses all possible rules. That's exactly what it's doing here. It's using...
Wait, this is a line. Just moving left or right. It doesn't change colors.
That's correct. That's what happens if it has... Oh, no, that I see. S equals 1 and C equals 1. That's an S equals C equals 1 case.
So that's a line. That's not that complicated case.
Why is this copy not working? Oh, gosh. Something is really wrong with the way these graphs are being rendered. Really wrong.
Looks like it might be a problem with vertex shape function.
Well, it's possible something was changed there. No, wait. Which is a problem with vertex shape function? The problem with the rendering time, or the problem with the incorrect rendering of the incorrect rendering of.
And with the structure for these graphs.
Yes,
so there shouldn't be a
there's
problem
no.
with rendering
What
function.
is Mano referring to? Is she referring to the case? I think you're referring to a different case, right? You're referring to the thing we were seeing before, the error we were seeing before, where it was not rendering the states correctly.
Yeah, it
Right?
seems to be.
Okay, so what I've been talking about here is why is this rendering so slowly in the case where we have just the graph structure.
Gotcha.
See what I'm saying?
Mm-hmm.
Okay, so this is one state, but two colors. But now I suppose we have the absolutely minimal case of which we should just enumerate all of one state, one color, right? So here I want to go C0, C0, correct? Is that correct? Wait a minute. Wait. What happened here? Look at this case here.
Well, there are two copies of the same rules.
But we shouldn't have that. That should never be done. That's not a subset. Oh, gosh. We want subsets without duplication. Do you understand what I'm saying? But how could
well, they should be without duplication unless it duplicates in the list itself.
Okay.
Do a tally on our original list.
I'm just going to do a union.
But why would there be duplication there?
There won't be duplication there. So how come this is a duplicate?
Huh.
Okay, let's look at this. Is it really a duplicate? Yes, it is.
Can you map tally over those subsets?
Why do I want
rendering
tally?
correctly? Well, counts or something like this. Maximum of counts.
That's right.
So there are no duplicates.
That's correct.
So it means either it's copied incorrectly or it's rendered incorrectly. Wait a second, subsets, or no, never mind.
Okay, let's
Can
go
we
back.
render all of them and see which ones? I mean, we need to find the text form of it.
Well, you're saying if I take this and I map it over this thing here,
Right.
what the heck is going on in a case like this?
So exactly. So can we see what it corresponds to?
Yeah, we have to find out what part number this is. 14. Oh, come on. What's going on here?
Tell you work with graphics.
Why wouldn't it work with graphics?
Well, there's some randomness in there, I'm not sure.
No, you know, it might be sizing or something. Okay. Well, look, here's the first case, right? So this case is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Case 11. Oops. I am totally confused.
So the color should change in one of them. I see. So my fix is not correct after all. Apparently it does assume the unique in the code.
Well, I think the problem is, you know what it is? It thinks the color, it thinks it only has one color because the left-hand sides have at most one color. Do you understand what I'm saying?
Oh.
Right? It's
Can you add
inferring.
another role to it which has a different color? I mean, I'm wondering if it just
I know what it's doing.
It duplicates them.
Look, it's got to decide how many colors there are. If it was black and white, it would have to decide how many colors there were, right? Do you understand what I'm saying? And so then it's got to know what the maximum value is, and it's deducing that from the left-hand side rather than from both sides.
Yeah, that seems likely.
Okay, so now if I add a rule, if I do this,
Well, I guess as a workaround, we can add a fake rule to all of them. And if we then change plot range to hide it.
Yeah, well, there we go.
Yeah.
Okay. But now, so look, one thing we probably should do, I mean, arguably we should just have a family of NDTM functions, but I just want to do this one here. So this one here, let's see, where was our big computation there? And anyway, I don't want this. I just want the rule there. And now this is rule cases 1, 1. Okay, So this is all trivial. So in the case where there's genuinely just, okay, so that here, these have rendering bugs. Okay. So the case 1.1 is trivial, which is not surprising. One state, two color. Let's just summarize what happens for one state, two color. We do have things like this for one state, two color. Right? But those apparently, okay, so what we need to do now for these cases is see what the head motion is for these. Am I making sense? Or alternatively, okay, what we really want are those old multi-space plots, right, which we never really figured out how to do to indicate, right, to indicate both the spatial structure and the multi-way structure, right?
Right.
I'm just amazed. I mean, I'm sorry. I'm really surprised. I've never looked at these before. I'm really surprised at how complicated they are. But I'm equally surprised about how simple this structure is. You know, how simple the growth is. See, I'm really confused here.
We really want you to find one that's so beautiful that you burst out crying.
Ed, okay, okay. Let's just look at this. Okay, can you understand
It's
why?
probably not that complicated. I mean, look at the rule, so it can move, but only
well,
once.
If we didn't have that bug,
that's why.
Mano, could you look at can we look at the code of multi-way Turing Machine and see if we can fix that problem with the rendering? Because that's what we really need to be able to see what's going on. But go ahead. You were going to say, I mean, here, we can take this rule here and we can just do this one in the case, I mean, it'll be a mess, but we can do it.
So the point is that if we delete one of the rules, then the result in multi-way system is going to be a subset.
Yes.
So if we then look at the first two only, we see that it can expand in both directions, leaving another color, or it can go back but only once. So we can probably plot that case just to see what happens.
Okay, here's a question. You guys, Jonathan, I guess, isn't here, but maybe we could invite him. Maybe can somebody see if Jonathan's available? Jonathan just got this result about semi-rings. That the set of multi-way graphs, multi-way systems form a semi-ring. So this business about adding a rule is going to be a story of those semi-rings. Am I making sense? Right? Adding a rule.
I don't really know what semi-rings are.
They're rings without inverses of some kind, I think. Okay, well, anyway, let's take that particular rule. Which one was it? It was the second one of these. Let's see what happens if we try and do this with oh, for goodness sake. Now what did it do? Now they're absolutely tiny. So let's try vertex size. What happened here? What are these things doing? See this? Oh gosh, it needs to be vertex size And then we have that whole thing that I was doing up here, the beginning, where vertex size is that multiplied by, do you understand what I'm saying? Do you see what this is doing? It's getting the aspect ratio right. Right?
Oh, I see. How can you know what the length of it is?
Because it's the number of time steps. Oh, for goodness sake, come on. This is crazy. Oh, now, what the heck happened there? What happened there? Okay, what's happening here? This is we need to have in here a thing that converts from the string to the actual expression form. Do you understand what I'm saying?
Not really.
Oh, okay, never mind. Okay, anybody know why this is failing? Let's try moving the graph layout thing here. Still failing.
The question is why the first one not failing?
This one here.
No, I mean the first, I mean the initial condition. I see. So if the initial condition is not failing, it means that the multivariate system produces states. So apparently the rest of the states are not in a valid format. So it cannot render them.
Yeah, I understand.
So it's probably not just a rendering issue. It might be an evolution issue.
Let's hope not, because then everything we've done is wrong.
Oh yeah, it doesn't seem wrong from what we have seen.
Well, let's see what in this plot here. Let's take this thing, and then let's say what is the vertex list here? Okay, those look like perfectly valid Turing Machine states. So I don't understand what's happening here. But okay, so let's write the code.
Can you verify that they actually lists and not strings with lists?
Oh, I think they are strings.
All of them?
All of them.
Okay. Well, I don't know. Can we render them in a simpler way? It's just using.
Or can you
vertex
apply
labels?
the Turing Machine shower to those?
What?
What's used to do the top of that graph? There it looks correct. What part of that code does that?
It's the same code. It's the same code, Ed. It's the state rendering function in multi-way Turing Machine. Okay, this shouldn't be any different. I mean, there's some bug here, and maybe Mano can go track it down, but maybe offline here, and see if we can fix multi-way Turing Machine. But for right now, let's do the following. Let's simply get, as an indication of what's going on, we can just look at the head position. We can plot the head position. Okay, so let's make a thing that says NDTM head position of, and then what we want to do here is rule I guess init and then t, and then that will be essentially resource function of this thing, and then no states graph, and just that number of steps. And then what we want to do for each of those, we want to get the head positions for each of those. So that is basically, for each of these, it's hash sub. Okay, so do you understand what this is doing? Yes, no, maybe. Right, you got what this is doing here, right? NDTM. Come on, guys, please. Oh, let's do the case. Let's write this one without an init, just because I want to. Okay, let's say 3 steps. All right, you understand it's getting that? Yes. So how do we get the head positions from that? Answer: we take like this thing sub 2. Okay, so the head positions are here, right? So where are those head positions? Can somebody figure that out, or am I figuring out everything here? It's this sub. Each one, first element 1, 2, right? Is that right? Nope, obviously not right. But oh, I see what the problem is. Then this thing here, they're strings, right? So each one of these is, so under map to expression onto this at level 2. And then I want to get, okay, so here now is that, and then I get that. Okay, so then I do this. At each level, I'm going to do that. Okay, so here, what? What is that? That should be the head positions. Do you understand what this should be?
The tape positions.
I'm sorry?
This look like the tape positions.
Tape configurations.
Right.
Okay, so let's look at this again. Okay, so let's take this, and now let's map hash 1,
Looks like
2.
There's multiple lists there.
Well, of course there are multiple lists.
Okay.
Oh, I see what you're saying. I see what you're saying. I see what you're saying. We want to do this. Yeah, you're absolutely right. It's this. Oh, the 2 expression wants to do that. I think I just want to say this, don't I? Am I wrong? No, there we go. Okay, so those are the head positions. Right, so for this particular rule, we could say, for each of those head positions, we could make a histogram of where the head reached. Right? Am I making sense? Okay, can you make sense of this? Let's go to 10 steps, for example. We could also, I suppose, do a gray level plot of what the configurations look like.
Might also be good to do array plots for each run.
Yeah, that's what I'm saying. What do you mean each run? No, there isn't an each run, because each run you mean what we could do. Look, remember, okay, so look, here is for each tape, NDTM tapes, right? And that will be, which position is that? That will be
the second position. Just 2.
Okay, so now if I just say NDTM tapes, okay, what do you think I should do with this?
Array plots.
How can that work, Ed?
Just map array plot to
Oh,
those.
you mean wrap array? Oh, okay, so that's not, I should do that still. Yes, okay, all right, okay. So that's showing us in the, let me just run it a little bit longer. I see, that's showing what tape configurations can occur, right? Right?
Yeah, yes.
Right? Boy, it's not helping me very much. That's somewhat complicated. Okay, so let's remind ourselves, in this particular case, other than this bug, what did this one's, okay, so if I say states graph structure, I'm just reminding myself, in this particular case, what did it look like? What? Really? Oh, I see. This was this one here. Okay. That was this guy here. So it's almost as if it either goes to the left or to the right. It never goes to both the left and the right. Am I making sense?
Try it with the first 2 rules first.
Say it again?
And first of all, we really do need to see the rule, which in this case will work. Yeah, and then try to run it with the first 2 rules only.
Run the multi-way graph.
Yeah.
Okay.
Okay, so you can go in 2 directions from the beginning, and then it can go 1 step back. But once it goes 1 step back, now it's on a yellow cell, so it cannot do anything anymore. So the difference that the third one makes is that once it's on the yellow cell, it can go all the way to the left until it exits this yellow zone, and then it keeps, and then it merges back.
So that's why in this case we see a little bit of, crossover onto the other zone, right? But otherwise it's just going in one direction or the other. Is that correct?
Yeah, I think so.
Okay. All right, so what was the next non-trivial case? These were all, let's remind ourselves, these were all with one state cases, right? And we still don't know for sure. Like if we take this case here, let's look at this case here just as an example of one that has a more complicated tree structure. Okay, so that's the 4th case of these. what an incredibly silly way to do this, but at least we won't make a mistake that way. Okay. So let's look at that one. So we know that one is kind of complicated. So let's just look at that for, let's say, 7 steps. Really? Maybe it had to go for 10 steps before it got non-trivial. Oh, this is going crazy. Okay, there we go. So that's 10 steps. All right, let's see what that looks like in terms of these traces here. Wait a minute. Did I do something completely crazy here? Is NDTM rules... Oh my gosh, we burnt in a rule here. Fortunately, it was the correct rule for this case here. Guys, are you paying attention at all? Sigh. Okay, can we please, like, come on, guys.
All right.
So that's wrong. But this here, I don't get what this is doing. Anyway, okay. Ah, no. Let's say, because this is going to get really big, let's say just 6 steps. Let's go more. 8 steps. Oh, come on. What is this doing? So it's not quite a binary counter. It's not quite getting all of them. Not quite sure what the ordering of these is. It's another issue. Let's go to 9 steps here. That's a somewhat complicated set. Right, and this is already somewhat complicated here. See if we can go to a few more steps, like 12, for example, here. Well, it has some limiting distribution. Not clear what it is. So, I mean, if we were to think about this like a kind of quantum system, hi, Jonathan.
Hi, sorry I'm late.
Well, we started, let's see, 2 hours, 15 minutes ago. You missed a lot of extremely boring stuff. But
one thing I might look for is whether how much these different Turing machines overlap in their histories.
Yeah, we could look at that. The basic thing we're looking at is non-deterministic Turing machines, and needless to say, the complicated behavior occurs even in cases simpler than I could possibly imagine. Right now, we're looking at one-state Turing machines, which I didn't think would ever do anything interesting. That is behavior from a one-state non-deterministic Turing machine. Jonathan, you're supposed to be at least mildly surprised.
I'm sufficiently surprised that I don't have a comment. I don't really understand how that can happen, but maybe I need to look in more detail at what this is.
Well, it's a two-color, one-state Turing machines.
I see. Okay.
One state, one color doesn't.
Yeah. Okay. Okay. That
add up
makes
to
sense.
anything.
So you're thinking that 2,1 is maybe the threshold for universality in NDTMs?
Well, this would be 1,2. This is one state, two colors. No, I'm not convinced of that yet.
Okay.
But it is a conceivable possibility, which would be kind of wild. And the thing that I'm looking for here, that the bigger picture is trying to understand how you compute meaningful things. Assuming that is a threshold of universality, how do you do a meaningful computation? And by the way, these systems are they are halting enabled, so to speak. They can end up in configurations where there is no rule, so they can halt.
I see, but they look. I mean, that thing there looks weakly normalizing. Am I?
I don't know if it's normalizing. I don't know.
Because I mean, without knowing the explicit step numbers, it's hard to say. But it looks like there are infinite paths and finite paths. But maybe that's just an artifact.
Yes, but I mean the finite paths. Maybe I don't know the definition of weakly normalizing. I thought that I see what you're saying. Yes. There are both finite and infinite paths. Yes.
Right.
I'm sure that's the case.
Yeah.
Right. So that means there are halting states that get thrown off as the thing evolves.
Right. So in that sense, they're just like combinators.
Well, yeah. I mean, but yeah. I don't know whether that's a useful comment, because the only way people know to do computation with combinators is with, halting right now. I mean, maybe if we succeed in proving the universality of the S combinator alone, there will be a different form of computation there.
Well, I mean, as we've discussed, halting and normalization are not necessarily the same thing. Well, normalization is a form of halting, but you can have forms of halting that are not normalization.
Absolutely. But that's the bigger picture challenge is to understand how to compute something useful. Like for instance, okay, one of these machines could factor numbers, and it could be the case that every path dies out, except the path that corresponds to the factors lasts a bit longer, or some such other thing, has some kind of tagging.
Right.
But the point of these is to understand this in analogy to I also wanted to kind of understand the quantum, the chemical, or whatever cases of this. But the first step was just to understand the zoology of non-deterministic Turing machines. And I had been looking at the 2-2 Turing machines, and with 2-2 plus 1, so to speak. 2-2 as in all the cases of two states, two colors, and then adding one additional non-deterministic element, and those are incredibly complicated. So
I forget, were those the ones that Simon was studying at the summer school?
Don't know. Could be. Don't know. It's possible. Yeah, if that's I don't know. I don't know. I should look at his. Yes, I don't know. Listen, we had a bug in multi-way Turing machine. It's doing.
Yeah. So do you remember that that vertex shape function bug that you forwarded to Charles and Kate?
Yes, I do, but this is more than that bug, because this is not only, look at this. This has undigested entrails, so to speak, inside each state here.
Yeah, that's not looking too good.
But I don't know what, I mean, let's take out, yeah, I don't understand why this one. Now notice what we're doing here is we're doing one rule at a time, multi-way Turing machines. Do you get what I'm saying? Yeah.
I mean, as is the case with all of the multi-way system suite of functions. The non-generation.
But I can do them in gulps, right? It doesn't really matter to the multi-way Turing machine whether, for Turing machines specifically, whether I put two distinct ones of these left-hand sides in the same bucket. It's not going to have make any difference.
Mm-hmm.
I mean, let me just try putting two in a bucket. Okay, so there's two in a bucket. and still get the same undigested stuff inside. Why is that happening? Because we did get results where it works. I mean, so
can you send me the code for this?
Yeah, this particular thing.
I mean, any of the ones where you're getting undigested stuff.
There's an undigested thing.
Thank you.
Wait a minute, Max, is it possible that your supposed fix broke this? No, that one works. Okay. All right, so look, the thing we're trying to understand here is for these one-state Turing machines, let's go back and look again. I mean, I'm not super hopeful that these one-state Turing machines will have really non-trivial behavior, but it's hard to explain even what they do right now. Should we look at some more of these, or should we look at, we could also look at the case. Okay, these are the 256 of those, but now we've also got the case, which we could also look at, which is, no, these are the two rule, wait. Which case is which here? This is the two rule case, right? Then we started looking somewhere down here. I mean, what is this? This is a different case here, isn't it? No, this is the three rule case, is it not? Guys, are you like here? Okay, this is the two rule case. This is the three rule case. So this is the three rule, 2, S equals 2, K equals 2 case. That right?
Looks right.
Okay. So then we looked at, after we looked at that case, we looked down here.
Show Jonathan that complicated one quickly.
Which complicated one?
The one that with the squiggly line on the top.
Well, you're asking why does it have a squiggly line? Yeah, Jonathan, do you have any opinions about that? It's a layer plot.
Well, it's just using plain old layered digraph embedding.
Yeah.
So I don't. If you just take that pure graph object and you sort of replot it with layered digraph embedding, does it have the same thing?
This is layered digraph embedding.
No, I know, but I mean just to make it clear that it's nothing to do with multi-way Turing machine. If you just take that object and you put it in graph with graph layer.
I'm pretty sure it will be. I did see this before.
I mean, if I just say index,
also to a
graph,
less
for
extreme
example.
extent. Yeah.
Why does index graph take a non-trivial time to run on this thing? Well, actually, we already see the result there.
Yeah.
It's a little weird. I think we should ask about it. Let me just.
It's very decides layer by layer where to go.
Okay, let's look at the next case, which was. So this case. Wait a minute. That's a case with three rules. Okay, 2, 3 rules. So now one state, two colors. Now we want two states, one color. One state, one color is hopeless. So the next case is two states, no, which way around is it? I did one state, two colors. Now I want to do two states, one color. I think that's hopeless, but go ahead. What were you going to say?
Sorry, just on the undigested states thing, if I put your rule and the initial condition into Turing Machine, it throws an error. That's what's causing the problem.
I see, because Turing Machine uses its rule digestion system to determine the number of colors. And its rule digestion system is getting indigestion on these rules that aren't...
well, there's not a match between the the left-hand side and the right-hand side, so to speak.
No, the problem is that it's trying to canonicalize the left-hand side. It's being too clever for its own good. It's insisting on a complete deterministic Turing machine for the left-hand side.
I see.
So that's a thing. Look, between Max and Mano, maybe you can go look at that internal code and see if we can just fix that.
Yeah, but as far as I can tell, nothing should be wrong. Nothing seems to be wrong with the actual evolution or with the rendering code. It's just Turing machine doesn't like that input.
Okay, so let's now look at this case here. 2, 1, 2. Okay, so this is now one color. All right, so that at least explains that. Direction there. Oops. Okay, so that's the cases. This is the case. Okay, so now we just want this. And we have all kinds of errors with all cases 2, 1. Okay, now just render without rendering some stupid giant tree. Oh my gosh. Okay. I got a few little caterpillars, which I think are fairly trivial. Okay, anybody think, have we seen one like this before? I think these are going to be the most trivial cases of the ones that are. Okay, I don't understand why this goes a fixed number of steps and then comes back to nothing. Oh, no, I don't understand that. Anybody understand that?
Does it go a fixed number of steps?
Let's find out.
I think it's extending every time.
Oh, look at that guy. That's very jolly. Do you think that's going to make a grid? Let's find out. Wow. Crazy. It's crazy. It's also crazy that I've never looked at these. Of course, nobody else has either, so whatever. Okay, so these are various kinds of ribbons. I've seen those kinds of ribbons. I saw those in the Rulial multiway and in the Rulial Turing machine case. Okay, look at these. Okay, let's get those cases out. All right, how much do we want to try? 8? Wow. All right, do you understand why? Okay, so basically what's happening is it's going some number of steps and then it's sort of giving up. It is normalizing. These are in a sense.
Well, it can go to the left or, well, somewhere, but then it can also come back at any step. But once it comes back, it cannot go anywhere anymore. So this looks like.
Okay, but I mean, what's kind of interesting about this? Wait a second. Why? If I go more steps, the onion is getting bigger. I do not understand that. Now remember that the initial condition is getting longer, right? Because of the way I'm doing this. But I don't think that matters because the head can never reach that. Why would that matter? Do you understand what I'm asking? Why is the onion getting bigger between these two cases?
These are not arranged by generation.
So what?
And so new vertices might appear not at the end, but somewhere else.
But so what? I mean, this is, oh, you mean that, wait a minute. I see what you're saying. I see what you're saying. So this is, so what you're saying is that if I did, I see. So you're saying if I did graph layout is layer digraph oops.
I think the onion is very similar to the case on the left, except it's kind of doubled. And this case is pretty easy to understand.
Right. It, in fact, it's almost drawing in the multi-way system what's happening in space.
Probably,
is that true?
yeah.
Okay, but I don't understand how, if I have...
Because the number of steps to go to the left is the same as the number of steps to go directly to the bottom.
I see.
And it can connect. So the maximum path length here can be larger than the number of steps because it can connect to an intermediate step from another path.
In other words, it can have a branch like... What are you saying there?
No, not necessarily branch like. I mean, I'm just saying it can, because it deduplicates states, it can connect to an intermediate state from another path.
Can connect.
Which is why if you go to the left and then you go to the right and then you go to the bottom, you get the path which is essentially 3 times larger than the step count.
Can I simplify this dramatically?
Yeah.
Rerun this experiment with an evolution graph structure and you'll see what's happening.
Oh yes, that will give us generations.
Really? Wait a minute. Should I do it?
Well, except it doesn't deduplicate all the states anymore.
What happens if I don't do layered graph plots here? Oh boy. Is there any way to untangle these? Let's look for these things.
What do you want to disentangle? I mean, this is just illustrating exactly what's happening.
Explain.
Well, because you're merging, because in the states graph case, by the definition of a states graph, you're merging elements across all time steps. You can have that there isn't a unique assignment of a time step to each state, which is why you're getting that veering off to the left and the simultaneous growing of the right. But if you only merge on the same time step, you don't see that. That's all that's happening.
I understand, but I'm still not... What thing are we trying to explain? I'm trying to ask, is this behavior trivial? And this picture does not look trivial to me.
I think we need to, if we see the rule and we understand why it's doing it, then we can say it's trivial.
Well, fair enough, but I want to see it from these pictures.
Well, I mean, I think it is trivial, but we only
so the point that you're making here in this picture...
Yeah, this I don't completely understand.
Well, but what you're basically saying is the thing evolves to a certain state on one path, and it can.
Yeah, but it can return from it at any point.
No, I mean there's no definition of time other than essentially evolution time. So, in other words, from any given state, the state just looks around and says, "Where can I evolve to?" There's no, I mean, this is our version of time for actual physics that we'll be using here. Whereas one can imagine an implementation of a non-deterministic Turing machine where time works in this way instead. Am I right?
I'm not sure what does it have to do with time. It's a question of states deduplication.
Well, okay. The thing I'm trying to understand is, in one case, there can be a state that was produced at step 3 or something, and then that state can do nothing for a while, and then can be reused on a subsequent step. If you're thinking about the steps as being applied externally.
Oh, wait, hold on. These are states, not expressions. So they are used by themselves. So I don't know what you mean by it holds for a while and then is used.
Well, I know they're just used by themselves. By the way, I wonder what the causal graphs look like for these cases. Are they going to be amazingly complicated? Oh dear. Well, maybe they're going to be very complicated. Is that illuminating?
Not that complicated.
Actually,
Well, it's essentially the same.
Let me try running it for like 6 steps or something. I mean, this should be very similar to, my gosh.
Well, I don't even really understand what they are for the multi-way case.
It's showing both branch-like, both it's showing both time-like and branch-like causal connections, right?
What do you mean by
branch-like? No, what I mean by that? I mean.
Might it make sense for me to describe how my own code works?
Sure.
Okay, so the way that the causal connections are defined for multi-way Turing machines is that you have creator and destroyer events for 2 separate objects. There's the current collection of states and colors, and then there's the current state of the tape. And so the tape is treated as a spatial arrangement. And so, anytime a symbol gets deleted or written, that's, a creator, a destroyer or a creation event. And then the current state of the head is treated as an atomic thing. So anytime that gets modified, there's also a destroyer and a creator event associated with that.
Is that compatible with what happened in the NKS book? I think in the NKS book, I was mostly doing mobile automata, not Turing machines. So I didn't have a separate state.
So if you had a trivial head state that didn't change, it would reduce to the mobile automaton case. I was going to implement an option that let you do, one or either, but I haven't done that. It wouldn't be too difficult.
Okay, well, maybe Mano could take over some of this code and introduce such an option, because that would be, okay, so this is causal connections are made depending both on tape state and head state.
Yeah, and so the consequence is that the modifications to the head state are generally trivial. Generally yield trivial causal connections, and modifications to the tape state aren't trivial because they have a spatial structure.
Right. Right. So, let's see. So here, what are we doing here? So again, I don't completely. Okay, I was gonna look at this business about the head positions and so on. Let me just look at that here. This is Okay, this is for head positions and, okay, so let's look at that for our onion, for example. Actually, we could just do it for, well, I guess we'll do it for all of them. Why is that coming out in that weird light font? Anybody understand that? Looks like a bug to me. See that? Just see what happens if I... That's just weird. I'm going to report that. I also don't know why it's purple. What's the syntax error here? Do you understand my question?
I don't think there is a syntax error. Looks like the boxes got messed up for some reason. If you retype all of this, I bet it will disappear. You might need to send the code for the whole cell because this might not have enough information.
Yeah. Oh, great. Why did that happen? Why does it beep? Like it's not, doesn't have contain any data. I can do the cell. Well, let's see if this works. There we go. Okay, that's the head positions, which seem uninspiring, to put it mildly. I can't see anything from this. Let's see. Let's see. So now this is NDTM tapes. What? What did I get wrong here? Anybody got any ideas?
Maybe try putting the slot in curly brackets.
That shouldn't be necessary here because NDTM tapes. Each one of those, let's look at one, okay? So NDTM tapes of this oh wow, they're all blank. Oh, I'm stupid here. Of course they're all blank because this is a one color Turing machine. See what I'm saying?
Yeah.
But we're still not completely clear why. Okay, in any case, so look, the basic point here is we've got something somewhat non-trivial going on, even with 2 colors, 1 state. Although it is my strong suspicion that we need 2 colors, 2 states to have something interesting. So what we looked at previously was we looked at all, back up here someplace, we looked at all 3 rule. These were the non-trivial cases from 3 rules, 2 states, 2 colors, 3 rules. Do you see what I'm saying? Yes? You guys remember that?
Yeah.
Okay, so the next case to look at, if we're not happy with these, although there are clearly some non-trivial things here, but we don't know how non-trivial. But the next thing we want to look at as we approach, would be, I guess, 4. So these were 3. My gosh. Those were all the cases for the 3 rule, whatever case. How many cases are there? Binomial 32 choose 4 would be, oh no, not this stupid thing. Okay. I don't want all of that stuff, but no, come on. Okay, this we already did. Okay, so now this case here, 35,000. You want to try doing those? So this, let's see how we can simplify this. Or is there a way to make this less grotesque to look at? I think what we should do here is, at the very least, we should just have this as a click. Because there's going to be 35,000. Oh, it's not going to be 35,000 cases because we're combining all the ones that have.
We also don't need to look at the rules.
No, we certainly don't need to look at the rules. But so what we want to do here is this arrow. We're going to do this arrow, that rule. And then we want to do that. Then we want to say all right, let's do it. Oh no, come on. Why is that doing that? Okay, let's do this case. All right, so there 35,000 to run. Let's just try running it. We might want to reduce the time constraint. We could also just, well, okay, this is tooling right along. We could also look at use just the number of states as a proxy for whether they're different. Do you get what I'm saying? I mean, how bad do we think that's going to be? Rather than using canonical graph, do you understand what I'm saying? No?
Using canonical graph makes sense.
No. I'm asking a different question. If instead of using canonical graph, which we know to be very slow for the big cases, if we instead simply look at states counts list, okay? We're not looking at the graph structure. We're just looking at the total number of states after t steps. The question is, if we find that there are cases where there is the same sequence of numbers of steps, number of states after t steps, the same sequence, a sub t or something of that, but yet the behavior is somehow different. Do you get what I'm saying?
Well,
Yes, but we're a third of the way done already.
Yes, thank you, Ed, for that piece of
but obviously that will
Well, we
depend.
don't
Sorry, please.
we don't know how many of them aborted.
it doesn't matter how many, but well, that's going to affect the that's only going to affect the rendering. See, okay, so let's just understand. Ultimately, okay, so how many cases were there? There were 8. No, how many in the original rule cases? How many cases are there? Are there 32? Do you understand? In this case here, how many of these are there? 32, right? So that means there are 2 to the 32. The total number.
By the way, sorry, to answer your previous question, as I was trying to say, whether you can have whether you can have non-equivalent NDTMs which have the same states council list sequence is obviously dependent on whether you include step numbers or not.
Let me see. Walk through that. So you're saying if
you don't
yeah.
include step numbers, then because of isomorphism testing, you can have semantically different TMA.
Sure. No, I know that. I realize that. I mean, I can't imagine that it would be distinct.
Right, but you have a better shot of distinct. It's a more distinguishing metric if you do the states council list with step numbers enabled.
Right, that makes sense. Okay, well, we may try that if this somehow messes up. Let's see if this can get to the end here. But I mean, just of the 32 cases. So right now we're at 4 out of 32. And we don't even know for sure. Oh no, I see. So okay, what we were doing before, we were taking the 4 complete rule cases that fill out a 2-2 rule set, and then we're adding one more on. So that's essentially the 5 case, but this is a simplified 4 case, right? So this is because this case could have a different collection of subsets. Am I making sense? So in other words, in the usual case, we have rule case 1, 2, 3, 4, and what they map to. And then we have one additional rule case, right? That's the 2, 2 plus 1 case, right? Make sense? Yeah, I'm going to give up in a minute here. Are you guys here or not here? I just don't know what, I can't tell.
Yeah, I'm here, but my dog's going squeaky squeak and bark bark.
Okay. Well, all right. Did you understand what I said? Yes, no, maybe. Do you have a comment about what? Someone was commenting on a live stream that how can it make sense that Turing machines at this level of, this is computation in the wild. This is not computation where we know what the Turing machine is supposed to do. The surprising thing that I discovered 40 years ago now is that it is very common in computational systems that very non-trivial things happen even when you didn't design them to be non-trivial. And that's what we're looking at here, is where the first non-trivial things happen in non-deterministic Turing machines. Okay, this stupid thing is probably trying to render 35,000 complicated trees. But can we please go back to what I was saying before to see whether we actually understand what I was talking about? Right? Did you understand the whole thing about different rule cases and whether you take one copy of each rule case? Okay, so you can have a subset where you require there to be at least one copy of each rule case, right?
Okay.
Or you can have, and that is the case that I was looking at previously, where we require at least one copy of every rule case. That is the 2, 2 plus 1 set of rules. Do you understand what I'm saying?
So each case except for one, for which we have two possibilities.
Exactly.
Okay.
And that has like 31,000 rules. Okay. Now, what we're looking at here is something where you can have 0 through how many right-hand sides are there? Are there 4 right-hand sides? No, there are 8 right-hand sides. So there's 0 through 8 possible cases of each rule case. Does that make sense?
Hold on. So you're doing subsets of 4.
No, in this case, I'm doing subsets of 4. I'm saying in the general case, if we got all the way to the 2 to the 32 cases, we would achieve that by specifying for each left-hand side, right, between 0 and 8 things on the right-hand side. Okay, so this case, instead of doing that, what we're saying is the sum of the numbers on the right-hand side is equal to 4 in the case that we're showing here.
Yeah.
Right? I wish this would come back. I don't know what it's doing. You know what? Could somebody go get John again, please?
I mean, it seems
I'm on
pretty
it.
clear what it's doing.
What's that?
I mean, it has a lot of pictures and it needs to render them synchronously, so it's doing that.
Yeah, but it doesn't usually. It shouldn't spin like this. This is a new problem.
What do you mean?
The fact that it spins for this long is a new problem.
But we don't know how many pictures there are.
I don't care how many pictures there are. It should not spin like this. It should be, first of all, notice that this isn't, this is not showing progress.
Even if you click on it? Oh, did it show progress before?
I think so.
Really?
I think so.
Well, maybe.
I mean, but the point is, it shouldn't spin for this long. I'm telling you, it's something to do with this stupid dynamic. Of course, it depends on the number of pictures, right? But this is wrong, and
I mean, it is possible that it's slower now. That seems likely.
Yes, I think there's a mistake. I think it was by somebody being too clever with these dynamic location things for graphs, and I think it's going wrong. Okay, well, anyway.
Check if there are any performance tests, but I don't know where to look for them.
Yeah, I have no idea. Well, I may just leave it running here. We may just want to wrap up. I can't even type notes about that 0 through 8 case.
In my view, the biggest problem here is that it's doing it synchronously. I mean, it can just show you below the cell that it's rendering it and let you do other stuff.
Yeah, I don't know why it doesn't render it. I think because it has to take, in a case of a list like this, there's no reason it should be synchronous.
I mean, I think the problem is that it needs to do it in a different thread, but because the kernel doesn't.
It has nothing to do with it. It's long outside of the kernel. The kernel already sent this data to the front end. That's what it means when it says formatting notebook contents. Kernel has nothing to do with it. It finished its work. This purely in the front end notebook system. And it's gotten slower. Okay. Well, I think maybe we should have to wrap up here. I will simply leave this running, and hopefully it will come back and produce an interesting result. Well, it's quite interesting. I mean, what we found here, this is all frozen, so I can't show you anything. But I mean, okay, maybe we can just talk for a minute if anybody has any ideas about, you know, we can look at the multi-way graph to get a sense of what's going on. The question is, what are our heuristics for figuring out whether something non-trivial is happening? Do you understand my question?
Yeah.
In the case of a deterministic computation, we have a pretty good idea how to do that. In the case of these non-deterministic computations, we would like some kind of multi-space representation. I mean, the only representation we have here is what this states graph looks like. So let's imagine, what could we compute with one of these non-deterministic Turing machines easily? Like, for example, could we do a language recognition task with one of these machines? What would that look like? So one issue here is that what I'm looking at here is always blank tape. So the input ultimately is non-blank tape. And so I guess the question is, for language recognition, what would happen is that the output would be something that has depending on the input, we would get different output. And what does it mean to get output? Well, one thing that could happen is it's a normalizing system and we have only one surviving state. Now, the question is, in one of these machines, can something interesting and faster than deterministic happen through it branching out into a large number of multi-way, a large collection of states, and then normalizing down to one state? Do you understand my question?
Yeah.
Jonathan, are you with us still?
Yeah, I'm here.
Do you have any comment on that?
Well, so in the case where the thing naturally normalizes, I don't think you can have any kind of speed up there, because there's if the system is strongly normalizing, then there will be both deterministic and non-deterministic paths that yield the normal form, right? Yes.
I claim that that's the case in the quantum computer case. That's essentially what is happening, is that you're trying to get, if we imagine a quantum Turing machine here, right?
Yeah.
The question
Wait,
is,
hold on. You can get new states with non-deterministic system, which don't exist for any deterministic one.
Yeah. Obviously.
Well, so what? Okay, Jonathan.
So it might not be faster, but you might get new results out of it.
One method for these that might be worth considering is doing a put append instead of a big rendering.
Yeah, I mean, look, this is just a bug. It needs to be fixed. Okay, there are lots of ways to avoid this. Probably there's probably a way to avoid it by using performance goal arrow speed rather than quality. It's just a bug. right? We need to just get it focused on and fixed. I don't think we should, we can hack around it in some way, but it's just a bug of some kind.
Anyway, sorry, what I was going to say was that in the more interesting case where you have weak normalization, so take like the prime example you gave earlier, where each branch is indexed by a collection of prime factors, and then if the prime factors multiply to produce the integer, then the branch normalizes. If it does, if they don't, then it doesn't, and so on. Then you have the problem, which is, I suspect, at a formal level equivalent to the other problem, which is that then to interpret the result, you have to essentially do a traversal problem over the evolution graph.
Well, let's talk about what that means measurement-wise, because in your interpretation of quantum mechanics, right, what you're saying is that the observer is doing some kind of completion, which in this system is an equivalence between Turing machine states, right?
Right. So that would be an effective rule that's added that if one branch normalizes and all others don't, it's an effective rule that gets introduced to essentially map all of the non-normalizing branches to the normalizing one.
Right, but notice in this case, it's a more extreme thing, because in the usual Turing machine rule, it is a one-cell Turing machine rule. Your observer rules are not one-cell rules. Do you see what I'm saying?
Right. They are, well, they could be, but in the way that they're most easily formulated, they're whole state rules.
Right. Right. But so let's understand what that would look like. I mean, so what we're saying is, if we imagine we're doing computation and we want to know what is the result of this computation. Okay. The traditional way to get a result is some form of normalization. Okay.
Right.
Fantastic. All right, let's just look at these guys. Since we got them with such effort, let's see what they look like. Okay, these are boring. Anybody tell me if you see something you think is interesting.
Okay, there are a couple interesting ones. Well, maybe I'm not as visually attuned to these things as you are, but there are a couple near the center left of your screen right now.
Those ones?
Well, yeah, actually, all of those that row of 5.
And I'd go 2 up from those.
These ones?
Yeah.
Those look like
trees.
But there looks like there's some sort of Fibonacci structure hidden,
yes,
which is why everything's lining up.
I don't think any of these are that interesting. The thing that I'd be looking for here, and by the way, it might not happen in a blank tape, is something where
okay, so just out of curiosity, what
like canonical graph failed to some extent.
Yes. Why don't we care about these? Because I've seen ones like these before. That's why I'm not making a big production out of them. I mean, like that one is mildly. It's just we've seen ones like that before. There's one that obviously was many copies of the same thing. I doubt that's interesting there. Let's do a scan to see whether there's any like super interesting ones.
Okay, I mean, like the one on the left, 4th up on the left. Why is that trivial?
This one here?
Yeah, for instance.
Because it's got a transient at the beginning and then it just trees out.
But it trees out. Is there merging going on the left there, or am I?
Yeah, there is, but only for the beginning. Then it just goes out, I think.
Okay, but there's merging happening after the first few steps.
Yeah. But then it trees itself out.
Okay.
See, I think the thing that's going to be most interesting is if it keeps. See, some of these don't expand terribly quickly. What I'm looking for is one that doesn't expand quickly and just has a lot of weird internal structure.
Right. presumably a decent metric is looking at the number of isomorphism cases and trying to make that some intermediate value between tree-like and
Yes.
graph-like.
Yeah, except
Wait, okay, no, and there are ones there that are definitely, those don't look like periods of transient.
these ones here.
I was actually looking at the ones on the right, just above those.
We've seen ones like that before.
But that's a longer period.
I sound like a zoologist here. That
looks like a longer and more complicated period of transient, though.
Yes, but I'm telling you, when there's something I think, I mean, those may in fact be interesting, but we don't have a way to tell that yet. I'm looking for something which is really, see, that guy is not, that I think is one of these onion-like ones. I'd also love to see a grid. None of those are grids.
We've had sort of ladder ones.
Ladders aren't grids. Nope.
Well, they're degenerate grids.
I know, but we've also seen ladders in simpler cases.
Okay.
See, something like this, I mean, it's probably not going to be interesting, but, boy. Okay, see, the reason it's worth scanning these quickly once is because sometimes there are like super interesting ones that show up. And see, that's probably not interesting. I'm going to add it anyway. That's probably one of those onion-like ones. You know, one could as well be looking at a tide pool. Try and find out whether there's... What's that?
You're less likely to get bitten.
In this case?
Yes.
Well, I think we just got bitten by this stupid thing doing, running forever. That was
I guess bitten by irreducibility is less painful than bitten by a crab.
Possibly, yes. I wonder what that does. It's probably not interesting. Probably just dies out. See, that's probably one of these. I'm going to look at that one, although I bet that one just dies out. But that has some chance to do something interesting and tangled.
Okay, so oh, sorry.
Yeah, go on. Did you see?
Okay, like 2 down from the one you just selected. How do we know that isn't growing a grid?
Because, well, we don't know for sure. It's my guess that it isn't growing a grid.
It looks like it could be. It's got 3 squares. All
right, we'll select it. I will give you good odds that it's not growing a grid.
I obviously I defer to your expertise, but
well, I don't know. I've never looked at ones like this before, so it's hard to know for sure. This is the point that as I say, that the mantra is the animals are always smarter than you are, and somehow they're even smarter than. I think that one is trivial. Even accounting for the fact that you know that the animals are always smarter than you are, they end up being, let's see.
Like the recursive definition of Hofstadter's law.
Which is what?
I'm going to misquote it, but it's something like, projects always end up taking longer than you expect, even accounting for Hofstadter's law.
It's like my friend Beatrice, who has a thing about medicine, medicine is always more complicated than you expect, even accounting for Beatrice's law. Okay, so that was okay, let's see. Come on, let's see anything else. Any other exciting creatures here? I can't believe I've spent so much of my life looking at arrays of pictures like this. what the heck is that thing?
Benzene. And near the right above your cursor there. Oh, wow, that's my cursor. Never mind. If you go over more to the middle, there's one that lines up well down kind of corner and up to the north. That one right there. No, that one.
This one?
No, the one next to it.
That one there?
Yeah.
Why do we care about that one? We've seen tons of those. It's as common as a
Okay.
If I knew my tide pool stuff, I could give good analogies. As a generic shrimp or something. Okay. I mean, go ahead.
Some of those at the third row from the bottom on the left, they look kind of like the subsets of Rulio multi-way systems.
Exactly.
But those are interesting. Those have non-trivial structure.
They have non-trivial structure, but they don't have. I mean, I think there will be ones here that look like the 3-2 Turing machine, that have that level of structure. That's what I'm looking for. But I might be wrong, because that may or may not occur in the case of.
But even having one of these that simulates a subset of Rulio space is already, I don't know, I think is already kind of interesting.
Oh, they're all subsets of Rulio multi-way system.
Yeah, but the question is whether it's a generator of Rulio space in some way.
Right. Yeah, sorry, I should have clarified. Yeah, of course, all multi-way systems are trivially subsets of Rulio multi-way systems, but those are large. Okay, those are generating larger subsets of Rulio multi-way systems than you would expect just from the trivial observation that they are, cardinality 1 subsets.
Okay. May I present your grid?
Yeah. Okay. Hypothesis falsified.
My benzene has not done anything interesting either.
Okay, that second one, there's still some merging happening. It's not totally tree.
No, but it's only merging at the beginning, I think. Maybe this side will go further. Let's try it. We can try it for a few more steps. Someone's asking on our live stream what's interesting about non-deterministic Turing machine, isn't any non-deterministic finite automaton reducible to deterministic finite automaton? Yes, but these are not finite automata. These are Turing machines, and there is no such similar reducibility. In the case of finite automata, it's an exponential reduction. Yeah, look, that one is definitely just, well, it's a transient. It has a ladder, but otherwise it's just going out in
Okay.
Well, this is interesting because this is not developing as interestingly as I thought it might, because I was looking before at the 2-2 case, where definitely there are significantly more complicated structures. The 2-2 plus 1 case. So just to comment on different cases. So what we had observed is generic altogether there are 2 to the 32 possible quotes 2-2 subset NDTMs. These,
by the way,
yeah,
I like that our naming convention for these rule classifications makes them sound like pseudo-Riemannian manifolds.
Which? What?
Well, sort of, 2-2 plus 1 and things.
Oh yes, that is charming. Right. Okay, these correspond to allowing between 0 and 8 RHSs for any of the 4 possible LHSs. Right? So then, oh gosh, the saving is going to take forever. No, it's not this craziness again. Okay, comment from Richard here. Quantum Turing machine needs states and alphabet set to be replaced by Hilbert space, the transition function, transition monoid, and the accepting halting space, the subspace of the state space. A question from Grateful Tomato. What if you used a randomly initialized tape instead of a blank tape? Yes, more things will happen in that case. I'm quite certain more things will happen. And it could be that, I mean, just to give you a sense of why I'm looking for something this simple, let me remind people of something that we already know. We already know that this Turing machine with 2 states and 3 colors is universal, and that's what it does from a blank tape. So it does something quite non-trivial. I wonder if I have a gallery picture here. Yeah, this is pictures of what that thing does just from a blank tape. Yeah, there it is, compressed, starting from a blank tape. Might remind you of Rule 30, and not for bad reasons. Now, we know that this particular thing, boy, I even had causal graphs for this. That's nice. Oh, these are, oh, yeah, I see. This is a deterministic Turing machine. Yeah, okay. So in any case, go ahead.
Multi-way causal graphs are basically never that civilized.
Yes. Okay, so the real question at hand is, this machine is universal. It's deterministic. What is the simplest universal non-deterministic machine? It's clearly going to be simpler than this, because we already know this one is universal. And so really, to go simpler than this, we're talking about probably 2 states, 2 colors, and some number of cases. This has 6 cases in its rule. And right now, the case we just looked at is kind of the maximal, pretty much the maximal simpler than this case. Namely 4. Well, okay, 4. We only did 4. We could have gone to 5 cases in the rule. Again, starting from blank tape. So that's why I'm somewhat optimistic that we're going to see something even starting from blank tape.
Right, but obviously the 2-3 proof doesn't, relies on not having a blank tape.
It does, but already the behavior, it happens to rely on not having a blank tape, but already the behavior is extremely non-trivial, even from blank tape.
Right.
And that's sort of the indicator that something interesting is happening. Now, in this case, for the non-deterministic case, we might need, see, the thing I don't really understand is how to think about, how to think about this non-deterministic computation. Because it isn't one of these things where, it evolves from an input to an output.
Well, but I mean, on that point, maybe it's worth addressing Richard's statement about quantum Turing machines. So if you take one of these, multi-way Turing machines and you construct the evolution graph, then that's a sort of, then each, for each step number, there isn't a unique state. There's a collection of states.
Yeah.
And each state is going to be weighted by its path weight in the multi-way system. And so then if you treat each of those states as being some pure state in a Hilbert space, some ray in a Hilbert space, then each of those level surfaces of the step number is an arbitrary vector in that Hilbert space given by a linear combination weighted by the path weights. Right. And so then the transition monoid becomes the rule that evolves from one evolution graph slice to another evolution graph slice.
Exactly. Right. So I mean, in a QTM setting, given a foliation effectively, or an evolution slice, and there could be multiple foliations that we could consider here, right? Look at the path weights. They define elements of a vector. The transition matrix, so to speak, matrix in quotes, maps from the sequence of weights at one slice to the sequence of weights at another slice.
Except that that's assuming that the slices are already saturated with all possible states.
Exactly. Right.
Well,
Right. Right. Assuming that every state is represented, albeit with weight 0, in each slice. So, I mean, again, my question is, assuming these are quantum Turing machines, I mean, the reading out of results from a quantum Turing machine is by a quantum measurement. And what's the difference between, and so how does a quantum measurement read out the results?
Well, so I mean, going back to that prime factorization example, right? That there's you could have a path that we know is the correct answer because it normalized, and we can have a bunch of paths that we know are not the correct answer because they didn't normalize. And so then what we want to do is add in, as you say, a collection not of Turing machine rules, but of whole state Turing machine rules that map the states on the non-normalizing paths to states on the normalizing path.
How is that going to help us?
Well, because then you're forcing the system to be strongly normalizing to the correct answer.
I see.
And again, thinking about this geometrically in terms of a Hilbert space, you're projecting onto that particular element of the eigenbasis, right? So if each path is a different element of the eigenbasis, you're by adding in the rules that map all of the non-normalizing paths to the normalizing one, you are taking that arbitrary ray in Hilbert space and you're projecting it onto the particular element of the eigenbasis that corresponds to the correct answer.
Okay, so let's write out for a second what we're talking about here. So in the quantum measurement analog here, what we're saying is in the Jonathan interpretation, you're getting a definite result by doing completions, by doing whole state. It doesn't need to be whole state, but it could be whole state.
Right. I mean, it should be stressed that completions are only one way of thinking about this. I mean, another way you can think about it is just you have an additional sort of automaton whose job it is to traverse the evolution graph and find the normalizing path. That's an equivalent way of thinking about the same thing.
Okay. Alternatively, an analyzer on the multi-way graph that finds the normalizing path or some other feature or it's just going to find some feature that we consider gets the answer.
Right, exactly. You have to define something. You have to define a success condition, and then you have some automaton that locates the path or paths.
Right. But what you're effectively saying is, I mean, the way to interpret that is brains, so to speak, are themselves running a multi-way computation, and they are capable of doing something like this. We are not stuck, our notion of definite things happening can occur even though that is achieved by us doing things which are themselves multi-way computations.
Right. And so, again, to relate back to Richard's point, when you have some arbitrary rewriting system, then obviously the set of strings that you can build up from its finite set of characters is a free monoid. Then when you add in rewriting rules, it becomes a non-free monoid. So then you have some arbitrary abstract rewriting system with a multi-way structure, with a non-trivial multi-way structure normally. Then the Knuth-Bendix completion procedure can be defined purely algebraically as an operation over that monoid. And effectively what it does is it reduces a partial, if you think about it in terms of QTMs, it's reducing the partial transition monoid of the QTM to a partial transition function of, or to an ordinary transition function of a standard, deterministic Turing machine.
Okay, so let me replay that claim. So your claim is the if you do enough completions,
right. I mean,
you
so
reduce.
This is a theorem in term rewriting theory, right? So what it says is, if we have some arbitrary finite state machine described by a transition monoid, and we apply a Knuth-Bendix completion procedure to it, if that procedure terminates, then the monoid is effectively reduced to a transition function.
Yeah, I get it. I mean, that's unsurprising. If you do enough completions, you reduce the transition function to a deterministic function.
Right. And that's just that's the term rewriting way to think of what we already know about convergence to single paths in multi-way evolution graphs.
Okay, but your point is this is a result from Knuth-Bendixology, so to speak.
Right. Yeah. In particular, the whole algebraic, Buchberger's algorithm Grobner basis side of Knuth-Bendixology.
Okay. How is that applied in our Grobner basis, in our use of Grobner bases in algebraic reduction?
So I asked Adam Stravinsky about this like 3 years ago, and I don't fully remember his reply. We are apparently using some form of Buchberger's algorithm, but I'm not sure whether it's the one that's isomorphic to Knuth-Bendix or a different one.
Yeah, for sure we're using that in Grobner basis reduction, but I'm asking what the interpretation of this reduction to a deterministic function is in the context of those algebraic systems. Right.
But that's what that effectively when you're generating the ideal that is the Grobner basis, that's the analog of your transition function.
Yeah. What's the analog? The ideal in the end, or what?
Right.
Okay, I think that's worth understanding at some point.
I think I have a notebook. Hang on, let me see if I can find it. It's been a while since I worked on this, but I think I have a notebook which shows how this works.
Okay, but in any case, I'm trying to understand, again, I mean, the reason that I keep on pushing on how do we interpret the answer is because I think it's also relevant to these molecular computation things, to the blockchain thing, to a bunch of different things. It's like, how do you, I mean, what we're claiming is there is sort of an analyzer that is being run on the system to determine, waving a flag and saying this is the answer. Just as in the case of statistical mechanics, I mean, one of the challenges is make sure that the analyzer isn't doing all the work, so to speak. What is the criterion on the analyzer to make sure that it isn't doing all the work of the computation?
Well, a simple one is that its computational complexity scales with a lower power or lower exponent or whatever than the actual evolution.
Yeah, I mean, the usual one in proofs of, if it is decidable, if it is a halting computation, then one says that it is, okay, but so, by the way, this is really the issue for quantum computers, is this exact question of whether the measurement, the analyzer, can be significantly simpler than the computation itself. Right? That's the question we want to answer there. And how do we answer that question? What is the traditional way? How did David Deutsch answer that question back in the day for when he was first looking at quantum Turing machines? Did he address that? Or did he just say, and then you do a measurement? I think he just said, and then you do a measurement.
Well, all work on theoretical quantum computer science that I'm aware of uses the standard, some variant of the standard, Hilbert space, von Neumann type formalization of quantum mechanics, or something that's provably equivalent to it, in which all measurements are treated as instantaneous projections.
Yeah, it's just wrong. It's just wrong. It's just wrong.
I'm sure that someone like Dirac realized that was an approximation, but I'm not sure that his successors actually have.
Yeah, I know. I mean, it's crazy. Like 40 years ago, the same exact issue came up. Okay, but with, for example, your completion interpretation, there is mechanics to the measurement. It is a bunch of completions being run. And, you know, there's sort of an algorithmic complexity. You could have a big bucket of just a ridiculous number of completions, in which case there's little computational work to be done, but there is high, you know, program complexity, so to speak.
Right, right. I mean, yeah.
But so how do we think about
we looked at with like Shor's algorithm, we were looking at, we were cheating a little bit and treating all measurements as occurring within one global time step. And so in which algorithmic and computational complexities were the same, because the number of edges you get is exactly the number of completion rules.
Yeah, well, so in other words, we're counting, in that case, we're simply counting completions to get us to a, you know, a unique final state.
Right, right. But obviously there are many more sophisticated things that one can do with that.
Right, but the thing is, I'm trying to understand, in the traditional formulation of quantum mechanics, how do we count the number of completions that are needed? Is there a way to do that based on the essentially the structure of the of each quantum state?
Well, it's going to be related in some nonlinear way to entanglement entropies. But until we have a general coordinatization theorem for branch yield space, I don't think we can answer that question.
Well, so let's just think about it qualitatively. So what you're saying is, to make a measurement, to get a definite result, if you have a branch yield space that is very uniformly covered, right? There's no redundancy in branch yield space in effect. Then it's probably very expensive to go and corral all those pieces of branch yield space together. On the other hand, if branch yield space is sparsely populated, it's like literally looking at essentially the entanglement entropy and asking, you know, if branch yield space is sparsely populated, it is much more plausible that you can have, even sort of at a Shannon level of estimating how much effort it takes, so to speak, it's much easier to corral it to a definite answer. Did that make sense?
Right, right.
So in a sense, the question of the effectiveness of a quantum computer is, given the output of the multi-way evolution, what does it look like in branch yield space? How high is its entropy in branch yield space? That's what you're basically asking.
Right.
And go ahead.
Sorry, do you mind if I very briefly share?
Go ahead. Go ahead. I need to go soon, but yeah, please go on.
Oh, sorry, not that. There we go. Okay, so here are the rules for doing Grosvenor basis reduction over arbitrary multivariate polynomials in some polynomial ring. Here defined as partially defined as equational axioms and partially defined as single-way operator theoretic rules. So then what's happening is when you do automated theorem proving over that system, the set of critical pairs that you need in order to make the system confluent is essentially trivially interconvertible with the generating set of that ideal. And then what we can do is, we can take like something like this. Let me see whether or not this actually works. Okay, this is not particularly interesting. Okay. In a moment, it will do something non-trivial. Maybe. There we go. Okay, this is a very simple sort of ideal in this monomial ring. But so then the completed form of this is the generating set for that ideal. And the interesting thing about that is it means that this causal graph informed version of doing Schutz-Bendix completion that we've tested out for ZX calculus should, I think, give one a different way of doing Grosvenor basis reduction. That's kind of dependent on the the sequence of firing of redexes in the polynomial ring.
Yes,
but I haven't looked into that yet. Someone should investigate.
Right. I would like to understand just this. Maybe I'll finally understand the structure of all these polynomial ideals and so on.
Anyway, there's some cool algebraic structure to these things. Is the point I'm making?
Right. I unfortunately need to go in a moment, but well, let's see. So just to review this again. By the way, we haven't even looked at the branchial spaces. Gosh, how could we not have looked at? Hold on, I just have to do this because this is necessary for my. Let's look at one of these guys, one of these somewhat non-trivial cases here, and let's look at the branchial graph for. Oh, don't tell me this is going to go into some stupid craziness. Okay, let's just look for these guys here, just for fun. Let's just look at their branchial graphs. So let's say branchial graph structure. And let's definitely not do that and not do that. Boring. What does that tell us? That probably tells us something. That those are all trivial.
Yeah, I think that's the basic conclusion.
Right. Well, that's a good indicator, though. I mean,
I'm going to 3 colors with that one.
That's a way more complicated issue, Ed. It's way more complicated. We can do that, but that's a more complicated story, which we're not going to do now. I just want to.
That would be a good hairstyle.
Depending, for those who have enough hair to do that with. Okay, I just want to make a branchial graph for this. This is going to be trivial, isn't it? I mean, we can kind of see it's trivial because it's basically just a tree. Yeah. Okay. Well, anyway, are these trivial in terms of branchial graphs?
I expect they would be, but by the way, I mean, do you want to compare the branchial graphs to the evolution branchial graphs?
What's an evolution branchial graph?
That shows ancestry distance between branch pairs in the evolution graph as opposed to the states graph.
Can I just type evolution branchial graph?
Yep. These will probably be more complicated.
Remind me what these are again?
Okay, so obviously a states graph doesn't have step numbers, an evolution graph does. So whether you treat a pair of states as being a branch pair depends on the ordering, the time ordering, and also depends on isomorphism testing, both of which are changed between the states graph and the evolution graph. So what constitutes a branch pair depends on which of the two interpretations you use.
I understand.
The standard term rewriting picture uses states graphs. The standard physics picture uses evolution graphs.
So what do I want to call this again?
Evolution branchial graph or evolution branchial graph structure, whichever you want to do.
Oh, well, those are more fun. They look very much like the actual multi-rate graphs. Perhaps that's obvious for a Turing machine. Okay, listen, we should wrap up, but various comments on our live stream here. Let's see, the Deutsch Jose algorithm is an interesting case, requires an oracle which doesn't decohere X. Yeah, I mean, look, I'm telling you, the reason it's worth looking at these things is because we are still searching for to get better intuition about what it means to do to do quantum measurement. And what we're seeing here is that, again, quantum measurement, okay, so, information theoretically information theoretically with some definition of information content, we can look at the redundancy of the, redundancy of the kind of the distribution in branchial space.
By the way, I mean, it's kind of an interesting idea that we might be able to treat the black box oracle in the Deutsch-Jose algorithm as being some kind of persistent topological structure in the multi-way evolution graph that doesn't thermalize.
Fair enough.
That's a cool idea, and one we should probably investigate.
But I'm interested in, okay, look, this thing about, how difficult is it to figure out what happened? And that depends on how spread out things are in branchial space. Not necessarily the distance in branchial space, but the distribution in branchial space.
Right. I mean, I think you both want to look at the raw number of states and and effectively the graph diameters, and have both of those be somehow intermediate between the minimum and the maximum, I would assume.
To achieve what?
To achieve maximal non-triviality.
I agree. To achieve the maximum chance to have a useful piece of quantum computing.
Right.
See, I wonder, in the molecular case, for example, I wonder what the analog of the branchial graph is. That's a common ancestor. That will give you, that essentially the analog is molecular distance, whatever that means. What is the distance between molecules? Well, you can think about that as, obviously the branchial graph is a common ancestry distance between molecules.
Is there not already some concept of molecular edit distance? Seems like something someone would invent.
Yes, there are such concepts, but they're not. It's not clear that they relate to sort of reaction distance.
Right. Well, yeah, I mean, because the edits are not defined irrespective of the actual, permitted sets of reaction.
Right. I got also some weird books about. One is called The Logic of Chemical Synthesis, and it degenerates rapidly into what amount to axioms, page after page of actual chemical reactions. So I don't know what to make of that. But anyway, I need to go. Great. Well, we got some things figured out here. Thanks, everybody. And thanks to people on the live stream. And we will no doubt see you in the new year.